In this video, we'll explore the Python memory management, understanding how Python manages memory, which is essential for writing efficient code. And in just a few minutes, you'll gain insights that will help you optimize your Python programs. So let's jump right in and demystify Python memory management together. Let's explore the two main categories of type checking in programming, static and dynamic. Static type checking involves a rigorous examination of data types at compile time. This means the compiler analyzes your code to ensure that the types of variables and expressions are correct before your program even runs. It's like having an eagle-eyed editor review your manuscript for errors before it's published. In static type checking, explicit type declarations are typically required. This means you need to specify the data types of variables, making it crystal clear what kind of data each variable can hold. It's like labeling every container in your kitchen with its contents. One significant advantage of static type checking is that errors are detected earlier in the development process. The compiler identifies type-related issues and reports them before your code ever hits the execution stage. It's like catching a spelling mistake before you print a document. In this type of checking, variable assignments are static and cannot be changed once that type is declared. This ensures that the data type of a variable remains consistent throughout its lifetime. It's like assigning a task to someone and ensuring they stick to it until completion. Static type checking often results in more optimized code. The compiler can make informed decisions about memory usage and execution, leading to improved program performance. It's like having a chef who knows exactly how much of each ingredient to use to create the perfect dish. Some well-known examples of languages that employ static type checking include Java, Haskell, C, C++, C#, Scala, Kotlin, Fortran, Go, Pascal, and Swift. These languages require explicit type declarations and undergo rigorous type checking at compile time. On the other hand, dynamic type checking occurs at runtime. This means type checks are performed while the program is running, checking the types of variables and values as they are used. It's like having a fact checker verifying information in real time during a live broadcast. In dynamic type checking, explicit type declarations are not required. You don't need to specify the data type of a variable. It can change as the program runs. It's like having flexible containers that can hold different things without predefined labels. One notable aspect of dynamic type checking is that type errors are detected later during execution. If there's a mismatch between types, you might only discover it when you reach the part of the code where the error occurs. It's like realizing you put the wrong ingredient into a recipe after you start cooking. In this approach, variable assignments are dynamic and can be altered. The data type of a variable can change during the program's execution, providing flexibility but also raising the potential for type-related errors. It's like having a chameleon-like variable that can adapt to different situations. Dynamic type checking may lead to less optimized code and the possibility of runtime errors. The flexibility in data types can introduce unexpected issues which may only become apparent when the program is running. It's like driving without a safety net, exciting but with higher risks. Several well-known languages use dynamic type checking including Python, JavaScript, Lisp, PHP, Ruby, Perl, Lua, and TCL. These languages embrace flexibility and let type checking during program execution. Understanding dynamic type checking and the languages that employ it is essential for developers as it affects how code behaves and how errors are handled. In the upcoming section, we'll delve into the intricate world of memory management in Python. Memory management is a crucial aspect of programming, and in Python, it's particularly interesting due to the language's dynamic and high-level nature. We'll explore how Python handles memory, manages resources, and keeps your code running smoothly. Let's dive into the fascinating world of stack memory and explore its key characteristics. Stack memory serves as the region where local variables and function call data are stored. It's like a storage area specifically designed to hold temporary data that's used within the functions you write. The stack memory follows the last in first out principle, meaning the newest data added to the stack is the first to be removed. It's like a stack of plates where you always pick the top one first. Stack memory typically contains primitive data types like numbers, booleans, and characters. These simple fundamental data types are efficiently stored in stack memory due to its fixed size and straightforward structure. One unique feature of stack memory is that its size is fixed at compile time. This means the amount of memory allocated for the stack is determined when you compile your code. It's like having a fixed size container where you can only put a certain number of items. Storing primitive data types on the stack is efficient because of the fixed size and simple structure. It allows for quick and predictable access to these data types, making it an ideal choice for such variables. Heap memory serves as the region dedicated to dynamic memory allocation. It's like an expansion playground where you can create and manage memory for your objects and data structures as needed. In the heap, you can store a wide range of data, including objects and non primitive data structures. This means you are not limited to simple data types. You can create complex custom structures and allocate memory for them here. Objects placed in the heap can have complex structures and variable sizes. This flexibility allows you to create data structures that can grow and shrink dynamically during program execution. It's like having a toolbox with compartments of different shapes and sizes to store your tools. One of the standout features of heap memory is its flexibility and dynamic memory allocation. You can create and manage memory for objects as you need them and release that memory when it's no longer required. It's like having a workspace where you can assemble and disassemble your projects at will. Let's take a closer look at memory management in action using an example. In this scenario, we have both stack memory and heap memory at play. In stack memory, we can have the main function with variables C and E. Variable E references an object in the heap memory, specifically the value 4. Additionally, we have the foo function with variable D, which references an object in the heap memory holding the value 2. Furthermore, the bar function has variables A and B, both referencing objects in the heap memory. Variable A refers to the value 4, while variable B points to the value 3. All of these functions and their associated variables C, D, A, B, and E fall within the stack memory. Stack memory is responsible for storing function call data, including local variables and references to objects in heap memory. Heap memory is where the actual objects are stored. In this example, it holds objects with values such as 2, 3, and 4. These objects can have complex structures and variable sizes, making heap memory ideal for handling dynamic and custom data structures. Garbage collection is a critical aspect of memory management, contributing to efficient memory utilization in your programs. Let's see how it works. Simply put, garbage collection helps free up memory that is no longer in use, ensuring it becomes available for other objects or data. Imagine it as a diligent janitor in a library. When a book is no longer being read, the janitor removes it from the shelves to make room for new books. Here's how it works. Identifying unused objects. When no reference is pointed to an object in a memory, it indicates that the object is no longer in use. Automatic cleanup. The virtual machine's garbage collector automatically steps in. It identifies these unreferenced objects and removes them from the heap memory. This process efficiently manages system resources. This system helps prevent memory leaks and keeps your program running optimally. Let's take a practical example to understand how garbage collection works and when it comes into play. In this example, we have three variables, A, B, and C. These variables were once referencing an object in a memory. The object's type is string and its value is my object. However, over time, the reference count of this object dropped to 0. This means that there are no variables pointing to it anymore. When no variables reference an object, it reaches a dead state and becomes eligible for the garbage collector. In essence, it's like a book that nobody is reading in the library anymore. Garbage collection identifies such unreferenced objects and clears them from memory. This process ensures that memory is efficiently utilized and that resources are not wasted on objects that are no longer needed. Let's explore reference counting, a memory management technique that keeps an eye on how often an object is referenced within the system. When references to an object are removed, the reference count for that object is decremented. This count reflects the number of active references to the object. Think of it as a keeping track of how many people are using a shared resource. Now, when the reference count reaches 0, it's a signal. This signifies that there are no remaining references to the object. At this point, the system jumps into action and deallocates the object from memory. It's like cleaning up after a party. Once everyone's gone, you put away the chairs and tables, freeing up space. In practical terms, consider a scenario where multiple variables share identical values. Instead of creating duplicate objects, Python's virtual machine is smart. It connects these additional variables to the original value stored in the private heap. It's like many people having keys to the same room, no need to make multiple copies of the same key. This approach is particularly beneficial in cases involving classes and scenarios where numerous references could otherwise consume a substantial amount of memory. Reference counting helps with more efficient memory utilization, preserving resources for other objects and ensuring your system runs smoothly. Imagine we have a variable, let's call it a, and we assign it to the value memory. In this case, a is referencing a string object stored in heap memory. This string object has a specific type, which in this case is a string. Its value is memory, and at this point the reference count is 1. The reference count indicates how many references are pointing to this object. In our scenario, it's just 1. Our variable a is the sole reference. Now, let's consider what happens when a is no longer referencing this string object. When that reference is removed, the reference count will decrease. Once the reference count reaches 0, it's a sign that no one is using this object anymore. The system will then take action to deallocate the object from memory. It's like checking a room after a meeting. When everyone leaves, you turn off the lights and close the door. This example showcases how reference counting helps efficiently manage memory. Instead of creating duplicate objects, it keeps track of references, ensuring that resources are used optimally. In Python, everything, even simple things like numbers, is treated as an object. When you write x equals to 10, you create an integer object in memory, and x becomes a reference to that object. This approach ensures consistency and flexibility in how Python handles data. In the example, when you execute y equals to x, Python doesn't create a new object. Instead, it creates another reference y, which points to the same object as x. Python optimizes memory usage by using the same object if it already exists with the same value. This efficient approach helps save memory and ensures that both x and y refer to the same object. In this scenario, when you set x equals to x plus 1, Python creates a new object which is the result of the addition operation. In this case, x plus 1. The link between x and the original object, which was 10, is disconnected. However, y still refers to the original object with the value 10. Python handles object references dynamically, allowing different variables to point to the different objects as needed. In summary, the choice between static and dynamic type checking depends on your project scale and needs. Python's dynamic typing offers flexibility while static typing provides extra safety for larger projects. Python's memory management, including reference counting and garbage collection, takes care of efficient memory uses. So whether you prefer Python's dynamic elegance or need the rigidity of static typing, and thanks to Python's efficient memory handling, you're ready for your coding adventures. Keep coding and exploring.